I'd like to talk a little bit about Poisson's equation and actually really Laplace's equation and the types of properties that solutions to Laplace's equation have. So Laplace's equation is the equation that the electric potential obeys in empty space where the charge density is 0. So any potential in empty space must solve Laplace's equation. Some examples that we're going to be considering just to have in the back of your mind for what we're looking at could be something of these two types or some other ones similar. So let's imagine on the left here we have, say, a grounded conductor. So it's grounded, so the electric potential is equal to 0 everywhere on this conductor. And then we have a point charge of plus q, some distance d, above that grounded conductor. And so above the conductor, there is no charge except where the point charge is. And so as long as you're not right at where the point charge is, Laplace's equation is the equation that tells us what the electric potential is up above the grounded conductor. And so ultimately, if we want to know what the electric potential is above the conductor, we have to solve Laplace's equation above there. Another example that we're going to look at is, say, this long pipe on the right here. And in this long pipe that's hollow on the inside, the outside is made up of conductors, and each side can be set to a different electric potential. So for instance, the top and the bottom here are grounded, set to electric potential of 0. And then the left and right side are set to an electric potential of V0, some constant electric potential. Inside the pipe, there's nothing in there, it's just empty space. And so the electric potential obeys Laplace's equation inside. Except for the inside of the pipe, you have to worry about the boundaries, namely the top and the bottom and the left and the right are set at particular electric potentials. And so we'll have to solve Laplace's equation inside the pipe subject to those types of boundary conditions. So these are types of examples that we're going to be looking at. As we're looking to solve Laplace's equation, there are a couple nice features that we're going to use as we're thinking about solutions. One we're not going to use too much, this first one. One feature is that the electric potential that is a solution to Laplace's equation at any given point is the average of the points around it. So if you imagine just looking at the electric potential at the center of this pipe, for instance, then whatever the electric potential is in the center is the average of the values around it. That's kind of interesting, but we're not going to use it too much. A more useful property is that the maximum and minimum values of the electric potential that solves Laplace's equation only happen at the boundaries. You can't have a maximum or minimum inside the region where Laplace's equation is valid. So we'll see an example of this in just a little bit, and it turns out to be super powerful. And then a final property of Laplace's equation that we're going to use is something called the first uniqueness theorem. And so one way to say this is that the solution to Laplace's equation with the electric potential specified on the boundary is unique. There's only one solution. Or another way of saying that is once you've found a solution that satisfies the boundary conditions, you've found the only solution that satisfies the boundary conditions and Laplace's equation. And that turns out to be super powerful. So if you can guess a solution by any means necessary, you've found the solution. Let's look at a simple example in which we can see some of these features at play, and we'll try and guess solutions or find solutions to Laplace's equation. So let's look at our first example. In our first example, we're going to be considering in only one dimension. So the electric potential is only a function of x. And in the setup I have here, imagine at x equal to 0, and to the left of that, we have a conductor, a grounded conductor. So the electric potential is 0 there. And at x equal to 1, I have another conductor, and that electric potential is 3 volts, for instance. And so that's all at the same potential there. And I want to know, how does the electric potential depend on the position x between these two conductors? So what we say is that the electric potential only depends on x, and then we specify the boundary conditions, the values of the electric potential on the edges, which is at x equal to 0, we have 0, and at x equal to 1, we have 3. Well, we have in between these conductors empty space, and so the electric potential must satisfy Laplace's equation. Since the electric potential only depends on x, this Laplacian of v just turns into a second derivative of v with respect to x, and that must be equal to 0. well, I need to solve this equation subject to my boundary conditions. What I'm going to do is I'm just going to guess something that I think works. So for instance, v of x is mx plus b, something like that. If I take the second derivative of that, I always get 0, regardless of what m and b are. So that looks like it's going to work as a solution of the second derivative of v equal to 0. Let me see if this can satisfy my boundary conditions. So if I plug in x equal to 0 in my guess here, then all I get is b. And at b, or at x equal to 0 rather, I should have 0. So that must mean that b is equal to 0. And my electric potential now becomes mx. So I still don't know what m is. So I'm going to use the other boundary condition to determine what that is. So at x equal to 1, my electric potential from my guess is just m times 1, or just m now. And that should be equal to 3, the value of the electric potential there. And so v of x should, in fact, be 3x. That satisfies my boundary conditions. At x equal to 0, it's 0. At x equal to 1, it's 3. The cool thing about the first uniqueness theorem is I just wrote down something simple and tried to find a solution to the boundary conditions that also solved Laplace's equation. And the first uniqueness theorem says, I don't have to search anymore. I don't have to worry. This is the only solution to this differential equation, to Laplace's equation, with these boundary conditions. So in particular, v of x is going to be 3x. That interpolates between v is equal to 0 and v is equal to 3. That's the only solution to Laplace's equation with these boundary conditions. And so that's pretty cool. I don't have to search anymore. Once I've found a solution, I have found the solution. We can also point out one of the other features of Laplace's equation, namely that the maximum and minimum only occur on the boundaries. We see that we don't have any kind of curve in between the left and the right-hand side of this region. We just have a straight line between x equal to 0 and x equal to 1. And so the maximum and minimum values that the electric potential can take only occur on the boundaries. Let's look at another example, which is also pretty simple, and in fact, even simpler. Let's look at that same one-dimensional example, except on both the left and the right-hand side, I'll have a conductor at v is equal to 0. So my boundary conditions are that v is equal to 0 at both x equal to 0 and x equal to 1. I still have Laplace's equation in between these two conductors, so I still have that the second derivative of v with respect to x is 0. Except now, rather than guessing the simple solution I had before, I'm just going to guess something simpler. I'm just going to say, what if v of x was 0 everywhere? Does this work? Well, it certainly satisfies the boundary conditions. V at 0 is 0, v at 1 is 0, because v is 0 everywhere inside here. It also obeys Laplace's equation. The second derivative of 0 is indeed 0, so it obeys the Laplace equation. It seems like it was a little bit too simple, but the first uniqueness theorem says that this is the solution. It's the only solution to Laplace's equation with these boundary conditions. In particular, we can't have some curve, like shown here in the dotted blue line, that interpolates between, or that ends between v is equal to 0 on both sides, and then maybe has some maximum in between. That would have a maximum and minimum on the interior of this region, and the maximum and minimum can only happen at the boundaries. And so this type of solution is not allowed. I'm only able to have the v of x is equal to 0 everywhere inside. And so that's the power of these features of Laplace's equation, that we can guess solutions to Laplace's equation. And if we guess right, then we don't have to do any more work. So I hope that helps understand some of the nice features of Laplace's equation.